Hello all, I am Syed Asrar, a PhD student from IIIT Delhi, presenting the project proposal titled Intelligent and Reconfigurable Deep Learning Augmented Wireless Channel Estimation at Edge. I completed my MTech from Jamia Millia Islamia and then joined IIIT Delhi as a PhD student in January 2021. My research interests are wireless channel estimation, deep learning architectures on hardware, reconfigurable architectures, and TinyML. I have a paper published in IEEE TVLSI, IEEE TCAS1, and several papers in reputed conferences. Dr. Sumit Darak is an associate professor in IIIT Delhi. He completed his PhD from NTU Singapore in 2013. His research interests are reconfigurable and intelligent wireless transceivers and algorithm to architecture mapping. I will start this presentation by giving a brief introduction of the field and explaining the motivation behind the proposal. Then I will introduce the problem statement and give brief review of the state of the art. Then I will give the detailed description of our proposed system design. Finally, I will briefly discuss project plan and then give the closing remarks. Wireless channels introduce fading and add noise to the transmitted signals. The cumulative effect of fading is represented as channel gain. Estimating the channel gain at the receiver using predefined signals known as wireless signals is called channel estimation. Channel estimation is particularly challenging in next-generation communication systems. The introduction of heterogeneous devices sharing the same spectrum leads to poor SINR, thereby decreasing performance. High mobility in V2X communication, large number of antennas in MIMO, and large channel matrix dimensions in RIS further complicate the task. Moreover, for complex environments such as mining and underwater communication, accurate channel models are often unavailable, making optimal statistical channel estimation difficult. Recently, deep learning based techniques have been introduced for effective channel estimation. However, integrating deep learning into wireless PHY is challenging due to low latency requirements of wireless communication. Additionally, most receivers are battery powered edge devices, necessitating low area and power consumption. Deep learning models are highly dependent on training, and those trained on one channel condition do not generalize well to different conditions. As a result, model trained on synthetically generating data may not perform well in real world scenarios, highlighting the need for training on real RF channel datasets. The lack of over the air datasets for channel estimation further complicates the problem. These challenges underscore the need for low complexity, deep learning based channel estimators and a testbed for creating training datasets with over the air signals that can also be used for verification purposes. The goal of our project is to develop low complexity deep learning augmented wireless channel estimators and demonstrate it for over the air channels in real radio environments. Our objectives are to propose low complexity deep learning augmented channel estimation techniques for CISO and MIMO OFDM systems using simulated channel models, build an RFSoC based testbed to generate training datasets for over the air transmissions that include hardware impairments and actual channel distortions, develop a methodology for training deep learning models using over the air signals, propose a low complexity deep learning model to enhance performance and further optimize it through quantization and pruning, develop and benchmark software and hardware IPs for both conventional and proposed models, create an RFSoC based end to end system level demonstration for real world radio environments. DL based PHY is attracting a lot of attention recently in both academia and industry, with 3GPP dedicating a working group in Release 18 to study AI/ML for new radio air interface. DL based solutions can be broadly classified as end to end solutions and block based solutions. End to end solutions replace entire transceiver with a deep learning model. While it provides global optimization, it requires a complete rethinking of a communication system design and is not compatible with the standard. Block-based solutions aim to replace one or more signal processing blocks with deep learning model. Replacing single or multiple models may provide better performance, but it requires a complex deep learning model. Augmenting a single signal processing block with a low complexity deep learning model is shown to provide better performance at low complexity cost, as it incorporates expert knowledge and thus is a preferred choice for hardware implementation. Our design falls in the category of deep learning augmented channel estimation. Our works have demonstrated that augmenting a conventional channel estimator with deep learning allows to use a low complexity model. Industry leaders including Nokia, Nvidia, Keysight, and DeepSeek have demonstrated deep learning based PHY in real world environments, tailored for site specific scenarios. However, these solutions replace multiple blocks in the receiver chain and thus do not obtain the channel state information. Some works have developed solutions using deep learning based channel estimation with over the air signals. For instance, deep Wi Fi employs a passive sniffing approach requiring two receivers, one closer to the access point and other farther away. The closer receiver acts as a label. While this method improves estimation performance, it is not scalable. Another example is channel former, which modifies the standard by sending double symbol DMRS with one symbol at high power to act as a label. This approach, however, requires standard modification and decreases spectral efficiency. In our previous work, we demonstrated that under simulated channel conditions, the performance of LS channel estimator can be improved by augmenting it with low complexity deep learning model. This concept was verified for various systems including preamble-based OFDM system, pilot-based OFDM system, and IEEE 802.11p based vehicular communication system. We are now extending the deep learning augmentation concept to MIMO systems. MIMO system require channel state information to generate pre-coding weights for effective beamforming. The process of obtaining CSI for beamforming purposes is called channel sounding, which occurs before the data transmission stage. In the state-of-the-art MLV-based solution, the entire OFDM demodulation and channel estimation block is replaced by a deep learning model. While this approach improves performance, it's extremely complex, requiring billions of MAC operations. We propose a ResNet augmented LS channel estimation called LS-ResNet, which reduces the complexity by orders of magnitude compared to the state-of-the-art. Simulation results verify that our proposed model not only performs better but also has significantly lower complexity. Next, we will further reduce the complexity using group convolutions, quantization, and pruning techniques. We will then develop efficient fixed point hardware IPs for the proposed solutions and benchmark them against state of the art. Our next objective is to develop a testbed for over-the-air training and validation of the deep learning augmented channel estimation. The biggest challenge is developing the dataset for over-the-air signals, as the channel impulse response cannot be known in real-world scenarios. We propose using the constellation points as labels for training the deep learning based channel estimator. During the training phase, predefined symbols will be transmitted, and the loss between the demodulated symbols and the known transmitter symbols will be used to train the model. Two datasets will be created, one using a channel simulator such as NVIDIA's Shona, and the other using over-the-air signals. In the proposed methodology, the training loop includes equalization and data demodulation as non-trainable layers, with only the DNN being trainable. The input is the received frequency domain data symbols, which are fed to the DNN to generate channel estimates. The DNN output and data are then fed to the equalizer and data demodulator to produce the demodulated symbols. The loss is calculated using labels, and the weights of DNN are updated using gradient descent and backpropagation to minimize the loss. The training will be performed in two steps. First, a synthetically generated dataset will be used, as it is larger and can provide a robust initial training phase. Then, fine-tuning will be performed using over-the-air signals. During inference, the trained DNN will be deployed between the channel estimator and the equalizer. Several architectures such as MLP, ResNet, and RNNs will be explored. The model that offers the best performance with low complexity will be chosen as the final model. An ablation study will be conducted to determine the optimal hyperparameters. Neural architecture search may also be utilized to find the optimal architecture. After selecting the architecture, quantization and pruning will be applied to further reduce complexity. When choosing the architecture and optimizations, the focus will be on selecting those best suited for FPGA platforms. After selecting the best architecture, the deep learning model will be mapped to a system on chip. This is a block diagram of our proposed system on the AMD Xilinx RFSoC. It contains an ultra-scale processor supporting the Python framework and an FPGA-based programmable logic, along with an RF frontend. The transmitter and receiver will be on the processor. The signals to be transmitted will be sent to the transmitting antenna via RF DAC and received via the receiving antenna, then sent back to the processor after digitization via ADC. For dataset creation, the transmitted symbol and the COM demodulated symbol will be saved. During inference, the received and OFDM demodulated symbols will be sent to the DNN module present in the PL. The output of DNN will be sent back to the PS for further processing. We have demonstrated the performance improvement of deep learning augmented conventional channel estimation for preamble-based, pilot-based, and IEEE 802.11p based OFDM systems, as well as the performance gain of DL augmented LS estimation for massive MIMO system. The next task is to optimize the deep learning model for a massive MIMO system and develop efficient fixed point hardware architectures through a hardware software co-design approach. For testbed development, the methodology will first be verified using simulated channels. The next step is to develop the RFSoC based testbed to generate the dataset and validate the approach. Finally, the system design for end-to-end PHY incorporating deep learning augmented channel estimation will be developed and its performance evaluated in real radio environments. To sum up the presentation, latency and hardware resource utilization are the main considerations in implementing deep learning in wireless PHY. Implementing the design on system-on-chip platform is crucial for a thorough analysis of performance, latency, and area utilization. Deep learning models are data dependent, so the training dataset should contain real RF signals. Generating a dataset with the actual impulse response of a channel is not feasible. Thus, new methods need to be developed to train the deep learning based channel estimation for over the air signals. We have been working on this project from last couple of years and have published 2 IEEE transaction papers and 4 papers in top conferences. We demonstrated this work at the VLSID 2023 design contest where we were runners up and the IEEE APC CAS design contest where we won the first place. Additionally, we presented at the PhD forum at VLSID 2024 and were the runners up. These are the references and thank you.